Hello friends. So in the continuation of CTQ series, today we will start a discussion of CTQ 12. Okay. So till the previous video, we have completed a lot of discussion about the CTQ 11. I think it was completed in the 5 videos parts. But yes, now we discuss the 12th problem. So what is the problem statement? The circuit is given. The amplifier was actually ideal, but I am considering here some practical amplifier. So the gain A I am considering, which later we can put infinite also. Okay. So here, yeah, 20 millivolt, some offset is given here in the amplifier, and we have to object the output voltage in the present scenario because we have the 20 millivolt offset voltage and two input DC voltage which are the zero point 0.5 volt and 1 volt. Okay, and amplifier is ideal. In the first case, I will consider A to be ideal. Actually, it is ideal in all the cases, but I am considering A here because I want to take it inside the calculations and later we will put it to the infinite. Okay, then output impedance, then input impedance. Okay, so let proceed one by one. So what we can see for it, if I'm considering the offset voltage here, then yes, we can simply apply the superposition principle as well to see the output voltage. We can apply the superposition principle to see the output. Okay, superposition principle. So we just consider simply one by one the inputs. Let's say initially the offset is zero. Let offset is 0 volt and our amplifier is an infinite gain. Then what we'll see, we will simply see 1k 0.5 volt. If I'm considering the offset to be infinite, sorry, offset to be zero, we can have this way. The circuit can be like this, 1k. Okay, so we can have the output simply. This thing we can solve by once consider the 1 volt to be shorted, then only we'll see the effect of zero point 0.5 volt. Okay, then in that case, what will be the output? If I'm considering one to be shorted, here is the ground. Then what is the exact input applied here? 1k zero point 0.5 volt and another 1k is here. Okay, so I'm just going through very basics. I am going through the basics. You people all know it how to solve. Let I will call it. Okay. So with the only zero point 0.5 input, I will consider the output coming due to the zero point 0.5 volt. What it will be? It will be minus R2 by R1 is what? 1 by 1. Two resistors are there. Okay. And what is the zero point 0.5 is multiplied here. So what we can see minus zero point 0.5 volt is the output due to this zero point 0.5 only. And the second voltage, what I will do, I will consider zero point 0.5 to be shorted. Okay. And consider only 1 volt. 1 volt is considered. Then what is this next circuit? We want to see it. This is the only circuit that we will have. Okay. If zero point 0.5 is shorted, I removed this means what I say offset initially is zero. Just it is a part of means superposition principle. But to look the circuit simple, I have removed it initially only. So here is what I can say 1k. Yes, this is also 1k. This is my output due to 1 volt only. So what will be output due to 1 volt is input times 1 plus R2 by R1 is what? 1 by 1. So it comes to be 2 volt. Okay. So we have seen two outputs due to two different inputs. Now we'll only consider third input, which is the offset voltage. Okay. So now what we'll do? Make the zero point 0.5 volt to be shorted. This is the only way of superposition that we want to see, and we can directly use all three voltages. We will see how to use it. Okay, then only network will be there. We'll use the network equation and then we can solve when we are applying all three voltages at a time. But here what I'm seeing here, I'm applying one voltage at a time. Okay, so now what I will do, I will consider only the offside voltage, which is nothing but 20 millivolt. Okay, so what is the circuit? Negative, positive. This is ground. 1k. This is ground. So This is the only voltage here, and this is 1k. Okay, now I want to see the output due to offset voltage. Okay, so the anyway the polarity doesn't matter for the offset, but time being I am considering it in this way, 20 millivolt. Okay, so how to analyze the circuit then? Because we are seeing that it is an ideal lamp, so this node virtual from the virtual ground it will be zero. Okay, so the just node connected to this amplifier will be zero. What I can draw the circuit again here. This is my amplifier, and this is ground. So this node will also be ground. That I should draw it some far away. Okay, so this is my 20 millivolt, and here I am having 1k to be 0. We are due to offset voltage. This is also 1k. Okay, so what I mean to say here, if my virtual short is applicable, then this voltage will also be ground. If this is ground, then what we can see, we can apply simply a means KCL network we can use here. But yes, if you want to, if you don't want to use even, then what I can say here, the current in this branch is zero. Okay, that's simple. So what is the exact network that we are seeing here? So actually, what is the network we are seeing here? 1k. So now it is only the point of your network equations, because this can be considered as the 20 millivolt in this way, and its other end is to ground, because we have seen from the virtual short, and this node is from ground from the virtual short. Okay, then what the other thing is there? Okay, so in this current is zero, and what is the rest is simple, this network 1k, and whatever the current will go through it, it will take inside this is my V out. Okay, the entire current will flow inside the amplifier. So whatever the current will come here, and it will go directly, whatever the current is coming here, it is going inside this amplifier. So there is no problem in this branch. So whatever the current is coming here, it will directly enter inside this amplifier block, which I am not drawing here. Okay, so that thing we can see now. There are two currents, because now, so what are the two currents? One current is this, and one current is this, and sum of these two currents is going to be zero. Okay, so what is this? 20 millivolt by 1k plus 20 millivolt minus V out due to this offset divided by 1k. This is going to be 0. Okay, and we can see, okay, this is the one current component I call I1. This is the one current component I call I2, and this the current through this 20 millivolt itself is 0. So from here we can calculate, what we can calculate, 40 millivolt is nothing but V out due to this offset voltage. Okay, so now the complete V out is what? V out due to the 0.5 voltage, which is minus 0.5 volt, plus due to this 1 volt, which is 2 volt, and due to this offset voltage, which is nothing but 0.04 volt. So exactly if I want to calculate from here, what you will see, and this is giving me the 1.5. So 1.54 is the voltage value that we are getting here at the output. So this is the like some sort of network and some sort of superposition. All means network. All what we have seen complete is a network. Some sort of superposition and KVL KCL. KVL KCL. So if I'm not interested to consider all these things individually, I can consider the entire network at a one time also. Okay. What we can see, if this is the 1 volt, 1k, 1k, 0.5 volt, V out. Okay, so directly we can consider the calculation for the V out here. What we will do, we will simply see here that this node is ground. Sorry, this node is at 1 volt due to the virtual short. Okay, let I call X. So Vx is at means 1 volt, and what the other thing? There is no current inside is 20 millivolt, and all the current whatever going through this one case coming inside this op-amp. So op-amp is taking care of that current. So again, we can consider a simple network. This is your 1K, and this side is your zero point 0.5 voltage. This is your 20 millivolt source, which is having other end at 1 volt, and other is your 1K. Its other end is at V out. Okay. So whatever the current coming in this way is going inside this amplifier, which I am not drawing here. Okay. So don't worry that where this output is not a floating node. Whatever the current going to the output is again coming back to the input of the coming back to the amplifier output. So we are not exactly entering inside the what is there inside this amplifier, but yes, it is something. It is a voltage controlled voltage source, voltage controlled voltage source. So it will sync whatever the amount of current it is going from here. Okay, so I'll let you know one thing here. If this is my difference voltage I'm applying to my amplifier, and what it does actually if we go inside it. So this thing I'm discussing because I don't want to make you confused, because you people may have that in the second network our node output is floating, and where this current or this 1K current is going where. Okay, it is not like that. So what is actually happening here, what is exactly we see, whatever the difference voltage we usually apply here, it's output version. What we see, this is the R out of the device, which ideally should be zero. It should be very small, and output should be what, A times this VD. Okay, and this is my VD. Or sometimes this point may ground. We can apply V in itself here, and whatever the voltage, we can have the two voltages in between these two terminals of the VD. Okay, so this difference is nothing but amplifier, and this entire structure is your the voltage control voltage source. Simply, we are applying the voltage input and we are observing the voltage output. Okay, so we are applying this voltage difference, which is a nothing but controlled voltage. So controlling voltage, controlling voltage, and this is your control voltage. So overall control voltage. So overall I can say it is a voltage controlled voltage source. So this is the structure of my amplifier. Okay, so need not to worry that where the current will go. So whatever the current coming from the structure, amplifier will take care. Okay, so this is the point I want to tell you here. Now we can simply apply this network, because this current is zero. So whatever the current in this branch, that I call the I1, and this is I call this I2. So overall we can see I1 plus I2 should equal to 0. So okay, so what exactly this node should be now? Now this node should be 1 volt plus 20 millivolt. So I1 is what? I1 is nothing but 1.02 volt minus zero point 0.5 volt, or I should do the 0.50 divided by 1K. What should be the I2? I2 then should be 1.02 minus V out divided by 1K, and this combination should be 0. And from here, what we can see, 2.04, which is nothing but 1.02 by 1.02 minus 0.50 equal to your V out. This is simple expression that we are getting here. So what we can see, this is nothing but, so it is coming what? It is right or something is missing here. 1.02. Okay, so 2.04. So if I'm doing 2.04, what we are getting? Mm, the output we are getting 4. Okay, 4 here, and yeah, 1. Yes, yes, exactly correct. So this is my V out. So that we are getting from the superposition also. Okay, so this is the output we are getting, and this was the exact number we were getting after superposition, and this is directly we are applying the network, and we are seeing that what exactly happening. So don't confuse with the output current which is flowing through the 1K register and coming inside this amplifier itself. Amplifier taking care for that. What is inside the amplifier, I'm not going again. We have seen a lot of things in the previous video itself and in the different series what this amplifier can be. It can be simply a what do you say? It can be any particular voltage amplifier structure, but just understand that it is a voltage control voltage source. So ideally, its output impedance should be zero, and whatever it is taking back, the current is taking back inside it. Okay, so now we'll see the input and output impedances. This is the till whatever we have calculated, we have calculated the output voltage. Okay, now if I want to see the output impedance calculation, then the impedance calculation is very simple. We know all know. Okay, so if this is the 1 volt for the impedance calculation, if I'm calculating the output, I will short it to one will be to ground, and what will be there? This is a 1K, and this is also to be grounded. 0.5 is to ground. So the point is that will the offset matter here or not? If I want to see the output calculation, then what we will do? Simply apply some voltage source, test voltage source, and we'll observe the test current. And simply what is R out? R out for the closed loop system will be dt by it. dt by it. Okay. So offset is not an intentional voltage. Then what we can see, we can make the input to be zero, but it should be there. It is an uncontrolled, or we can say it is already inside the device. But when we are looking for this output impedance calculation, then whether it should be zero or not, VUS should be shorted or not. Okay. So we can keep this short because we don't have to see its effect, what is happening with this particular thing. But yes, when we are calculating the output impedance, which is nothing but we are applying a small signal test voltage source and we are observing the current. In that regard, what we can see when we are calculating the small signal, when we are calculating the small signal impedance at the output, okay, VOS to be considered as the shorted because the reason is that what perturbation we are applying in terms of test source, it can be much smaller than this offset also. Okay, so this perturbation, VT perturbation can be much smaller than the any voltage available in the system. So what we can see incremental effect of all the DC sources, or better to say independent sources should be negligible. Okay, so if incrementally they are negligible, that's why we are considering voltage sources to be grounded and current sources to be open, because incrementally they are doing nothing. So overall, considering current source to be zero, the incremental effect of current source is zero simply in that particular analysis, considering current source to be open, and incremental voltage for the voltage source is zero simply in that particular analysis, consider this voltage source to be shorted. Okay, so this thing I want to tell you here. So now if you want to see from that perspective, then what is there? Okay, so where this current will go, let's consider the difference voltage. Okay, so for this because I'm considering my a term here, the gain I'm considering, as it is ideal for ideal this a to be infinite, but if I'm considering my a factor, and what I want to see here, I want to see the exact calculation for this. Okay, so what is happening here? What will the VD? Let's say this is my VD, and VD is simply the voltage at this node X. So if the so Vx is simple, nothing but VD. So what should be this VT? VT should be what? It should be minus 8 times your VD. This is one thing that we can understand from here. Okay. So what is the other? This is the one thing. What the other thing is that what is ID? Sorry, IT is what? IT is simply one resistance is there inside it. Let I'm considering the finite resistor. And what it will be? It will be VT minus the voltage that is inside it, which is nothing but okay. So for the time being, this is not a correct consideration here. Let I should let you make one thing more clear. So okay, it will not directly be out. It will not directly be the VT, but rather than it will be some other voltage. Okay, so I think something is missed here. So what I want to see, I'll draw the little bit inside it. What is an A block? Okay, otherwise you will be confused. What is the A block? I also drawn it on previous page. But whatever the input it takes, it has some output which is non-different from this VT. So sorry, which is actually different. But when we considering this R out of this particular amplifier to be zero, then it is non-different. Okay. So what I mean to say, this is the one voltage in nothing but ABD. Here the BD applied here. Here is some R out for this amplifier. Okay, here is my BT. So what exactly is happening here? Here my BT is applied. So actually looking, BT is different, and this is my IT, and some of IT will go inside it, and some of the IT will go in this 1K register. Okay, so rest circuit is we can consider. So just look at both the circuits at a time. That the point I want to tell you here. So what is this? This is the out that I want to see. I want to tell you P out. Okay. So what is this? This minus ABD is nothing but this is a V out. Okay. So now write the expression for the IT. IT is VT minus V out by R out. Okay. This is the one current component. What is the other component? Other component is VT minus Vx by 1K. This is the other component of the current. These are the two components which are contributing to their IT. Okay. So what is the this current component? Or current through this resistor is equal to current through this resistor because there is no current going inside this amplifier. Okay. So what we can other expression that we can consider the current VT minus Vx by 1K is exactly equal to Vx by 1K. Just a matter of network, you can see what we can see from here Vt equal to 2Vx, or we can see Vx equal to zero point 0.5 Vt. Okay, so this thing we can put inside it. So what is this IT? IT is your Vt plus ABD by R out plus Vt minus Vx. Okay, okay, it is also 0.5 times Vt by 1K. What is the VD? VD is nothing but your Vx itself, which is 0.5 Vt. So what I can exactly write the equation IT is equal to Vt plus gain times Vx, because Vx is equal to Vd, so 0.5 Vt by R out plus 0.5 Vt by 1K. Okay. So from here we can exactly write Vt equal to 1 plus 0.5 A divided by R out plus 0.5 Bt by 1K. So if I'm taking the Vt as a common, if I'm taking Bt as a common, then what is there? It equal to, if we take the Vt as common, then what we can see this as A is, now I will consider that A to be very large or A to be very infinite, means A to be infinite or A to be very large. I will consider now. So what will happen? 0.5a is much greater than 1. So directly I can ignore this one. So I can say 0.5a by r out plus 0.5 by 1k. Okay, so this is what when we take bt common. Okay, so what exactly happens actually, what should be there, this term should be infinite when we are putting the a to be infinite. Okay, so what exactly it is making me, it is telling this it should be infinite. So what is the r out I'm expecting, r out I'm expecting bt by it. If it is infinite means it is 0. So in the ideal case what we can see, the output impedance is to be 0. Okay, so this is the exactly what we are considering here. I'm considering the internal model of amplifier itself, and then we are calculating. But directly also you can see for any voltage amplifier, voltage to voltage amplifier, this particular topology of feedback, what we see, we usually see the output impedance is reducing in when negative feedback is there. Okay, so if simply I am telling you this is a voltage controlled voltage source. Okay, so whatever the resistor R1, R2, this is R2, this is R1, this is the input. Okay, so when we are looking for the output impedance R out, then there is one output impedance for this amplifier itself, let's call it small R out. Okay, so when we look for the complete R out, then what is this complete R out is? Complete R out is a small R out divided by 1 plus A beta. Okay, what is the beta? Beta is nothing but R1 times R1 plus R2. This is your beta. So from here what you can see, as A is to be infinite, what you will see, R out is to be 0. Simple thing. That is the one conclusion that we can draw from here. And you can also find the expression for this particular, what is the A beta and what is the beta here. You can see simply beta is nothing but a feedback component. Beta is simply when we are considering feedback amplifier, we consider this is the voltage feedback by voltage output. So what it comes when we put the input to be 0, input is 0, then it comes as 1 plus R1 plus R2. Okay, this is the beta. So input impedance, what will happen with the input impedance? So when usually we see from here, okay, so yeah, this is the R1 and here the input. So okay, this is my output. When we see input impedance from here, it looks to be infinite. Okay, what we speak of when we see the impedance from here, when we see the impedance from here, then what exactly will happen here? Because the amplifier is ideal, so this node is virtually short. Okay, for the ideal amplifier this node is virtually short, so Vx is your 0 for ideal amp. Okay, if Vx is 0, then whatever the amount of the perturbation we are applying here, the current is going this way, I1, the same current is passing through this. Okay, so no current is going inside this amplifier. So what should be the impedance actually when we apply the test source here at the, instead of input we apply a test source. So exactly the test current which is IT, this is my BT, this test current is passing through this, and BT, this test current is nothing but BT minus the virtual ground, which is means the node X by R1. So simply what is this? BT by IT is your R1 only. Okay. So when we look from the input, we usually get the resistance what is there as a with the source. Usually we see that only. Okay. Or what is the used in the negative feedback network, which is the R1 here. Okay, so that R1 comes as the input impedance, because due to virtual short the current flowing through the R1 is the only current generated by the source that we are applying a test source. Okay, So from that viewpoint, the another question, that is third question, from the zero point 0.5 volt, what is the input impedance? Then Rn comes as 1k only. Okay, and what is the R out impedance? We have seen R out impedance to be 0 for this particular configuration for the voltage control voltage amplifier. So I think I have covered all the things. We have seen the exactly what is happening inside this amplifier part, and we involved all these parameters in the calculation. Then we have applied simply a network equations. Okay, so this thing we have seen here, and what is the actually why should we means whether we should consider this offset voltage to be open, or it should be considered or it should not be considered. So I mean to say, when we usually see the output impedance, we are applying a perturbation that is a like a small voltage change, and we observe the current. So that particular thing can be very small. Okay, so I need not to consider any particular DC voltage inside the circuit when we are calculating output at any node. Because what we want to see, if we want to see from this characteristics, let there is some random characteristics, uh, IT versus VT. Okay, then what I want to see here actually, I want to see for very small perturbation. I want to see, let I want to see this okay, this is my del VT, and this is the current change I want to see. This is my del IT. Okay, so this itself will give me this IT, which are also called a Thevenin voltage, or we call the also this the output voltage here in this case. It is simply this del VT by del IT. Rather, I should say here the VT itself is my small signal quantity. So this is a small itself. Instead of saying to del VT, this VT itself is a small signal voltage. Okay, or I should say this IT dash and this VT dash. So here in my case, my VT itself is a small quantity, which here I've considered del VT, and IT itself is a small or whatever the perturbation I'm observing, that I'm considering del IT. So these two, the ratio of these two will give me this impedance at any node. Okay. So this thing we have considered. This is an internal structure of amplifier. And what else? Okay, these were the three things to consider. Rest many things I can consider apart from these, but I'm not considering here. I'm not willing to consider because it will increase the length of the video. But what extra thing that I can give you here to means understand, you can consider a little bit of frequency components here. Frequency components. What you can drive a resistive load also, or we can see some sort of resistance across this 1k feedback resistor. So and if this amplifier is non-ideal, or non-ideal means yeah, if there is a finite gain, and if there is some finite input impedance also, then how we will see all the calculations and how it will change. Okay, so this is the only thing that I want to tell you here. The rest, the problem was simple, and it was asked with I think it was asked in some interview. So it is very it's a simple. Just you must have the analysis and you must have the understanding of internal structure of amplifier as well, voltage control voltage source as well. Okay. So thank you. This is enough for this video.